Hello everyone, welcome back. So in the last video we were talking about complete projective measurement. Now we will talk about incomplete projective measurement, and you will see that the complete one is a special case of this incomplete projective measurement. All right. So let's try to understand first that let's say that I have a vector space V, and what I want to say is that this vector space is spanned by a set of subspaces which I can call E1 and a direct sum E2 up till ED. All right. So here in general E1 can be a higher dimensional subspace. What I mean by higher is that it's greater than 1. All right, when we were writing it in a basis in the previous case, like E1, E2 up till En, those were all subspaces, but they were one-dimensional subspaces. But now in general it can be higher dimensional as well. For example, if I have a XYZ three-dimensional space, this XY plane is a two-dimensional subspace of the bigger vector space. All right, so this is the idea that I can write it. I mean, if this three-dimensional space can be written like something like this, XY plane plus the Z space. All right, and this vector space, total vector space, can be broken up like this. All right, so now and let's point out to another thing, that is the projection operator pi I, which is a projection operator in the EI space, EI subspace. All right, so this is the idea. So from the definition of projectors, what we know is that pi I times pi I is nothing but pi I, because if you project in a subspace once, and if you do it again on that vector, it will remain the same, right? And we also know that pi I and pi j, when I is not equal to j, is equal to 0, because they are orthogonal projectors, and this will be 0. All right, so so let's say, and there's one more assumption, is that these subspaces EIs are orthogonal projections, so they are orthogonal to each other, right? So if so this is the same as this. All right, whenever your projection in one direction, once you project in j direction, then if you want to project in I direction, if this is 0, that means that they are orthogonal projections. All right, similar to this picture, xy is orthogonal to z. All right, so that's the idea. So now it's same as before, that if you do a incomplete measurement with respect to this orthogonal decomposition, your probability of getting EI, so probability of getting EI is, okay, let me write it in a proper notation. Probability of I is psi pi I psi. Okay, how do we see that? Because let's say that my psi is a three-dimensional vector. So in the XYZ plane, let's write it like that: AX plus BY plus CZ. All right, this is the XY Z example that we were talking about. So what I'm trying to say here is that if I act on it with the XY, this notation, by this notation I mean this is a projector in XY direction. So if this acts on psi, what you get is nothing but just the XY part of this vector. All right, and now if I ask you what is the norm of this vector, this norm, if you measure in this decomposition and you get you get this vector out. Okay, this collapses to this psi collapses to this vector. All right, and now if you want to take the probability of getting it, what you do is that you take the norm of this vector. So what you do is that pi xy, and you have a psi, and this gives you nothing but a square plus b square. All right, so that is what you're doing here. So here, so once you project out, it collapses to the vector, and then what you do is that you calculate the probability by taking the norm of that collapsed vector. All right, so let me write it down again. Probability of I is equal to, then my collapsed vector was this, so I want to take the conjugate, and then I'm calculating the norm here, right? So, but by definition, I know that pi I square is just pi I because it's a projection operator. So what you get is just pi I psi. All right, so this is the probability. And there's one more thing to notice here. If you check this example, you can see that here psi was normalized. That means that square root over a square plus b square plus c square is equal to 1, right? So it has collapsed to this vector. So now obviously square root of a square plus b square is not equal to 1. So your collapsed vector is not normalized. So you have to normalize it. All right? So by normalizing, I mean I have to rescale it such that it's a unit vector. Its norm is 1. So what I do is that my new collapsed vector, so my collapsed vector, vector is after measurement psi I, which is pi I times psi. Obviously this is not normalized, so what we have to do is we have to divide by its norm. By its norm, I mean square root of this psi pi I psi. All right. This is similar to what you do in regular vector. This is what you do with regular vectors. If you want, if you have a vector and you want to turn it into a unit vector, then what you do, you divide it by the norm of a, right? So you divide it by the norm of this one. But this is nothing but, let me remove this part. So, but this norm here is nothing but the probability I, right? So what you do is that you just write it as pi of psi divided by square root over probability of I. All right, this is my collapsed vector after measurement, and this is my collapsed vector, and this is my probability of getting that outcome. So if you are given this vector, your collapsed vector will be this one, but it will be divided by square root over a square plus b square. All right, then it is normalized, and you can see that when you're doing complete measurement, then you are collapsing it to one-dimensional subspaces. But when you're doing an incomplete measurement, you can do it like you collapse it in this subspace in the xy plane. All right, so complete measurement is a special case of incomplete measurements, and you can also see here is that the probability of getting this in the xy plane is a square plus b square. So you can decompose it into one-dimensional subspaces, calculate their probabilities. What I mean by that is that the probability of getting x is a square, the probability of getting y is b square. So the probability of getting into the xy plane is a square plus b square. So they are additive. So from complete measurement, you can trace back to incomplete measurement. The probabilities. All right. So I hope the idea is clear. Is that whenever I'm doing measurements, I don't necessarily have to do it in a one-dimensional subspace. It can be traced down to a higher dimensional subspace. By higher, I mean greater than 1. And then I can calculate the probabilities like this. and the collapsed vector is like this, and we have to normalize because I mean only normalized vectors make sense because we have the probability interpretation. All right, so I hope this is clear, and if you're still facing problems, then please ask us during the consultations. Thank you so much.